Okay, let's start our lecture number 16. Now we are in about 2/3 of our course on advanced electromagnetics, and today our plan is to go to those topics. You have we closed the last lecture by deriving Maxwell's equations in vacuum for magnetostatics, and we are going to do some quick applications of the integral formulation of those equations, and to show that in some very special cases they can let you calculate fields in a very simple fashion. Basically, we use Ampere's law and symmetry and superposition properties of the B field. Then we are going to calculate the vector potential for current loop. A current loop is a good model for the magnetic dipole. And we are going to use our advanced mathematical tools to do a general expression for the vector potential of current loop. This also has importance for antennas and other applications. Loop antennas, we have fields that have similar ways of calculating them. So then we are going to analyze another typo here. The behavior of localized distributions, magnetic dipole, and magnetization. We're going to talk about the magnetic dipole, which is the counterpart of the electric dipole in electrostatics. In magnetostatics, the lowest order contribution of material media to magnetic effects is the magnetic dipole. In fact, that's what atoms produce in terms of magnetic effects, right? You have orbital momentum of electrons around nuclei, and also have spin of the electron, which is also a state of rotation, let's say, of a charged particle. So those things are equivalent to magnetic dipoles. That's where magnetization of the material media comes from, right? And finally, we are going to talk about this concept of magnetization currents, and that's when we are going to finally derive Maxwell's equations for magnetostatics with or without material media, general formulas. And we are going to briefly comment on typical types of magnetic material. References for this class: Jackson, obviously, sections 5.5 through 5.6 and 5.8, and our ebook, sections 5.6 through 5.8. Just recall that what we derived in last class. Let's talk about field determination by use of the integral formulation. Well, we obtained two differential equations. One is the fact that the B field has zero divergence, is a solenoidal field, so no magnetic charges exist. And the curl of B is given by mu0J. And we introduced an auxiliary field, which is the magnetic field, H. In vacuum, we just introduced that that relationship in vacuum, B equals mu0H. And with the introduction of the magnetic field, the curl becomes curl of the magnetic field equals to J. J is the current, free current at the moment. Whatever current we have. But now we have in vacuum, so we have current produced by circuits, right? Mu0 is the permeability of vacuum permeability. I think I'm opening the wrong, just a second here. Which is 4 pi times 10 to the minus 7 Henry per meters. B field is measured in Tesla, Weber per square meter, and H field is measured by in units of Ampere per meter. Okay. And then we have, using our well-known integral theorems, we have from the solenoidal condition, we have that the Gauss's theorem we obtain that the magnetic flux net going outwards of a closed volume, closed surface, is 0, or inwards as well, right? That's the geometry to do the integration. And also from Ampere's differential form of Ampere's law, we derive, using Stokes' theorem, Ampere's law, which is for a closed loop that encloses, you have a closed loop here that encloses surface sigma, whatever, doesn't depend on J, okay, on the existence of a current. I mean, this is a universal law, doesn't depend on the existence or not of a current. It means that if there is a field, the circulation of the field is whatever current is enclosed by that path C. Even if the current is 0, it's going to be 0. If it's not 0, it's going to be different than 0. Doesn't depend on the presence of the current. Okay, so the area is always the area that's bound by that path C. So it's very important to observe this remark, because sometimes people make mistakes because they forget this important information. The area is always represents the surface bound by C. The path orientation is always defined according to the right-hand rule, so that you imagine a traveler on the path, going through the path. He has to go to a trajectory that has the area always on the left. So you have the right-hand rule to do that. So here are some situations we derived we showed in the last class. We quickly review here. If you have a path that is, you have a conductor in which it flows a current I. If you have a path that includes the entire cross-section, then the whole current is going to be enclosed, and you have Ampere's law yields the circulation of H equals to I. However, if you go through a path, oops, I think I lost synchronism here. Yeah. If you go through a path that has part of the cross-section, then you're going to have a current that's smaller than I. If you go outside, the integration area is this one here. That's the integration area. But across this area, there's no current, so the result is 0, right? So, in some situations, very specific and simple high symmetry problems, Ampere's law can be used to determine H given the current distribution, okay? We can determine that. But, I mean, to do that, recall that the unknown, let me go here, the unknown, which is H, is in the inside of an integral. So to be able to determine H using Ampere's law, we have to be able to remove H from the integral. So we have to know at least how H behaves on the path. For instance, I can remove H from the path if H projected along the tangent to the segment is constant. If we know that. So we have to have some information prior to removing H from the integral. So we have to know, have to be able to, by symmetry operations, okay, and using the superposition principle, we might be able to factor h out of the integral. So we have two things that we do. In fact, we are using Biot-Savart's law and symmetry operation to know, where h is constant, where the projection of h along the tangent to the curve is constant. So we have to use two things. One, use Biot-Savart's law, which means not calculating the field but superposing fields in a clever way so that we can determine what is the remaining components of the field. Okay, so Biot-Savart's law is just used to determine for a given coordinate system what is the remaining or non-zero components of the field. So that's the first thing we do. The second thing is symmetry. We make symmetry operations, make rotation, translation of the distribution, of the current distribution, and see if there is any modification in the distribution. So if we do that, we can determine that against those coordinates related to the symmetry operation, the field is not going to depend. Okay? So symmetry allows you to determine the coordinate dependence of each component of the field, and superposition using Biot-Savart's law, because it's essentially a right-hand rule, right? I mean, a current like this produces a contribution to the field, which is a right-hand rule. So if you want, you can replace this Biot-Savart's law here statement by right-hand rule. What is right-hand rule? Current element like this gives a field at this point given by that is oriented like that. But we use Biot-Savart's law because we have to know the dependence on the distance. So we have a localized, localized current element. Let's say J dV. That's the element that either IDL, JDV, or KD sigma. At a certain distance, well, you know that the field is going to be something like this. So, I mean, if that's a plane, that would be something like that. And depends on the inverse of this distance. Depends on the square, right? Inverse of the square of the distance. Inverse square law. So I have to know that. We have direction using right-hand rule for a current element. And depends on this, is depending on the distance, essentially. So equally spaced elements at a given point. So if I have another element here that is doing a JDV like that, the contribution, if the distance is the same, at least the magnitude of the contribution of this element, if this is the same, the JDV is the same, the magnitude of the contribution is going to be the same. The only difference is the direction. This would give a direction like this, right? So we have to, in 3D space, we have to calculate that, to know where the direction of the fields of each element is going to point, okay? So let's do some examples to show you. Let's look at this. I mean, we did that before by using Biot-Savart's law. Now let's calculate using Ampère's law, and we are going to show that the result is the same that we obtained before, but now in a much simpler way. I'm going to do the two things. So first of all, you have straight wire, right? Make a drawing here. You have a straight wire, infinitely long, And there is a current I, like so. So let's determine in the plane that cuts the wire in half. Any plane will do it, right? So we see that the cylindrical symmetry is the most proper coordinate system to be used here. So we have to look at, let's imagine an x-axis here, y-axis there, and z-axis is the wire itself. So the variables we have is r, right, the distance, phi, and z is the z coordinate. We want to determine, well, in principle, we don't know Biot-Savart's law. So we think, well, we're going to have a field that has three components, which depends on the three coordinates, right? So we have components and coordinate dependence. First thing is to determine for each component of this, excluding the natural dependence of the versors of the system on the coordinates. Forget that, but let's talk about the components of the fields. The components of the field, okay? So what are the dependence of these components? On what do they depend? What coordinates? So we do symmetry operations relative to r, phi, and z. So it means I'm going to make a translation along r, the radial axis, that start at the origin, right? I can only increase it or decrease it to 0. I'm going to make translation on the z coordinates. See if the distribution changes. And I'm going to make rotation on the azimuthal angle and see if anything changes. So does my distribution change configuration if I do these symmetry operations? It's the same thing. I'm here and I'm observing here. It's the same thing as I move in the point itself. That doesn't matter. I can have a point standing here and moving the distribution, or fixing the distribution and moving the point. There's no difference, right? Everything is relative. So let's try to make symmetry operations relative to the z coordinates. So it means that I'm going to make translation and see if there's any modification. So the first symmetry operation is translation along a direction that is parallel to z. So I have a stationary point and I translate my distribution along z. Well, if I do that, if my wire was finite, then no change would be observed. But because the wire is infinite, then, if the wire was finite, I would observe a change, right? If this pencil here, if I move here, the distance of the point to the pencil changed. Right? If I have an infinite wire, if I change, if I translate along z, the wire is infinite, so no change is observed. So first conclusion, no z dependence on the translation parallel to z. No z dependence. So I still have the three components, right? Because I'm just doing symmetry operations. I'm not looking at the field itself. So I have this. Second operation is related to my azimuthal angle. Okay? So I'm going to make rotation. I'm going to rotate this distribution. It's the same as rotating the points. Right? I rotate the distribution and observe if there's an effect. Obviously, the configuration is not going to be modified by doing that. So if I do rotation, right, on the phi variable, the phi variable, then we are going to be, the distribution is unaffected. So, conclusion, H field has only one dependence in principle. Right? So finally, I will make translation of the along the radial direction, which is orthogonal to the wire itself. So if I do that, I change the distance, right? Well, changing the distance, obviously we expected, because the quantity depends on the distance. We expect that there's a change in the quantity. So translation doesn't make translation along the radial direction affects the distribution relative to the observation point, right? So we reduced the component dependence, the H field components dependence, only to dependence only on one coordinate, which is the radial coordinate. So the symmetry is concluded. Now we do the superposition, and using Biot-Savart's, which says that the effect depends on the distance, and the direction contained in Biot-Savart's law is the same as right-hand rule. So if we go here, if we look at this point that we are showing here, this point, let's pick two current elements symmetrically located relative to the xy plane. So we're going to pick, I can measure here. At this point here, I have one element which is like this, the dl, right? So the contribution is IDL. That's the IDL plus, which is the one above the plane xy. So I pick symmetrically another one, which is like this. Same DL, same length DL. So I have to have the same magnitude of the source. So this is IDL minus. But you see that DL plus equals to DL minus. I'm just putting the sign to differentiate the location of those, okay? So let's look at the contribution of the field of those two, right? right-hand rule, we see that this is going to contribute, this one, by itself. It's going to contribute to something that is orthogonal, orthogonal to this plane here. Let me draw with a transparent system here. So I have this plane here. That's the plane. So I have a contribution for the one element alone, right, which is orthogonal to DL and orthogonal to this line, which is the right-hand rule, right? So it's going to be something like this. It's going to be this direction. So notice that this is at 90 degrees with that too, and 90 degrees because this line R is on the plane, and also 90 degrees with this line here, right? So one element, in this case, any element only gives a contribution along the azimuthal direction, which is given by the A5 versor. So the other DL plus also is going to give a similar contribution along the same direction. So you don't have to compose. Any element I give is going to give a contribution like this. So by superposition, we see that the field has only the azimuthal component. In fact, it's not that one. This one here. And the azimuthal component depends on R. So we know that H field is given by, after concluding the superposition principle, we have H equals H phi A phi. Now we have Ampere's law. Circulation of the field equals to the current involved. So C encloses sigma, right? So we have to find a path on which the tangential component of E is constant, of H is constant. Well, for me to accomplish that, I have just to fix R, make it constant. Making R constant means a circumference, right? So I use, for Ampere's law, making a top view now. Top view. That's the current. That's the current wire in the middle. That's the path. Let's make it a little better here, right? I'm going to use a constant radius. In other words, a circumference. Current is going up like this on the screen, from the screen, right? So in this case, I use let's say R0, right? I make on the curve R equals to R0, H equals to H phi of R0, A phi, and the L in this case is R0 d phi, A phi, and the integral in this case is going to be equals to I. So we have a very simple integral, right? We have integral. Integration variable is phi from 0 to 2 pi a phi of r0 times r0 d phi equals to I. You see, h phi goes out of the integral. It's going to be h phi of r0. R0 also goes out. So integral 2 pi is 2 pi. Of d phi is 2 pi equals to I. Then we have the result. H, or already the final answer, H equals to I divided by 2 pi r. Now I'm making r0 equals to r again to make it our variable, a phi. That's the result we have. Similar to what we have by doing Biot-Savart's law, right? There are not many problems in which we can use Ampere's law. Only those specialized distributions we can do that. The next one we are going to like to talk about is the one that we also did use Biot-Savart's law, which is that due to uniform distribution on a plane. Okay, we did that before. Now we're going to be a little quicker now. We know that this distribution is more convenient to use the XYZ system of coordinates. So the distribution has translation symmetry along the X direction, along the Y direction. It doesn't have translation symmetry along the Z direction. So we know that the components of the field that we have now, right, for this problem, H might have 3 components, which in principle depend on Z. Okay, so that's what we have from superposition. I'm sorry, superposition, symmetry, right? I'm sorry. From symmetry operations, symmetry. Then you go to Biot-Savart and right-hand rule together, or Biot-Savart if you want, superposition. I'm going to draw the plane like this, okay? I'm going to just make a line, which is the plane looking up front. We have several, as if we had an infinite number of parallel lines like this. Okay, uniformly distributed. Now let's put the ZX somewhere. Here is the Y. The Y direction, X direction coming forward against the screen, out of the screen. So we are going to calculate the field on the Z-axis because the Z-axis can be anywhere, right? Translation symmetry. So let's calculate. Let's determine, what is the remaining components of the B field, of the H field on the Z-axis. So what do? We pick 2 wires, 2 of those wires, symmetrically located. We already know the behavior of wires. So then we choose, something like this. Yeah, I think I'm gonna make it closer like that. That's one such element. The other we have, because Biot-Savart law specifies that the effect depends on the distance, we have to pick at the same distance because we know that we have the same intensity of the effect. So I'm going to pick here, approximately here. Okay. So right-hand rule for this wire here that comes forward is like this. The field is going to be like that. 90 degrees on this segment here. I mean, the field product is going to be at 90 degrees with this segment is going to be something like this. I'm going to draw it in red. Contribution, right? Let's call it 1. That's DH1. The other one is wire 2. It's going to give a contribution which is at 90 degrees. Same intensity. I'm sorry, this is wrong. Should be not up, but down. Wire 2 makes a contribution like this. Okay? Equally deviated down. By construction, if we make the vector sum of these two vectors, dh1 and this one is dh2, we are going to have a resulting field along parallel to y. dh, let's say. So the resulting field above the plane is to the left. If we make the same reasoning here, anywhere, right? The left wire is going to give a contribution to the, like this, and the other one is also going to make a contribution like this, and the result is going to be to the right. Okay? And also by symmetry, we see that at a given distance z, right? Just make the plane upside down, we expect those fields to be the same at the same distance from the plane. Right? So it means that, concluding, field has only one component, which is hy. And this component, the field has this property. The function hy of z at the same distance above and below has the same magnitude. So hy of minus c equals to minus hy of z. That's the property. Okay? So we can draw some conclusion using Ampere's law. I can make some specific cases here. For instance, I can make a closed path here, okay? Here, let's say Z1, and here is Z2. So here the field is going to be H has a component Hy of Z1, and here the field would have a component Hy of Z2. I'm pulling to the right, but it is to the left, so Hy is negative, in fact, okay? So if we make the Ampere's law for this path here, it means that the circulation of H field equals to 0 because there's no enclosed current. So make the integral, you see that the segments here do not contribute to the integral. So the only contribution comes from those parallel to y. So you're going to have, let's say, y1, y2. So you're going to have, let's call this 1, 2, and this 3, 4. Right? This is equals to integral from 1 to 2 of HDL plus integral from 3 to 4 of HDL equals 0. Okay. Integral from 1 to 2 equals to from y1 to y2 hy of z1 ay. Well, I just need the y component of the L, so it's dy ay. Hy of z1 goes out of the integral because the integral doesn't depend on z. So it's going to be y2 minus y1. Same way, integral from 3 to 4. It's going to be integral from y2 to y1. Ay of z2. Oops, is this positive or negative? I'm going now in this direction, right? But recall that the L is always, the general expression for the L is like this. The L equals to dx ax plus dy ay plus dz az. It doesn't depend on the direction on the path. You just use the expression. Dx equals 0, dz equals 0, dl equals dy ay. Doesn't matter what direction you are moving, okay? So it's the same. Integral from y2 to y1 hy of z2 dy. So it's going to be hy of z2 y1 minus y2. That's the result we have. So the integral is going to be integral of HDL equals to ay of z1 y2 minus y1 plus hy of z2 let me see, I think I made a mistake here. I forgot my sign. Oh, that's correct, yeah. y1 minus y2, right? This equals 0. So this is equals to, in other words, this is equals to minus y2 minus y1. If I divide by this, I conclude that ay of z1 equals to hy of z2, independent of z1 and z2. Right? Conclusion: on the above, on the upper plane, hy is constant. It doesn't depend on the distance because whatever z1, z2, h is the same, h is constant. Also in the lower plane. It's not the upper plane. The upper hemisphere. In the lower hemisphere, same behavior. Hy is constant. But we have to recall that Hy satisfies the property. It's constant on one side, it's constant on the other side. But Hy of minus z equals minus Hy of z. Right? Well, if Hy is constant, I can say that Hy can be written as a constant times something that changes signs together with z. So I can put here z divided by magnitude of z. So I can have that property. Hy has this behavior. Switch sign when you move across the plane. This for z different than 0. Okay. What happens that z equals 0? Well, we are going to discuss about it. Okay. We have a sudden transition, right? From one direction, suddenly change to the other one. Switch to the other one. So now let's apply Ampere's law. Now we are going to enclose one piece of the plane. Let's make a closed path here. Now I could now, I don't have to be symmetrical, right? I can make a closed path like this, if I want to. Because at this point here, we have a field. At this, we have the same field, but to the other direction. But I mean, I'm going to make symmetrical just to make it simple. We're going to enclose part of the distribution. Now we have this, integral. Now again we have y1 and y2. Now we don't have to worry about how high we are relative to the plane, because field is going to be constant. So those lateral segments do not contribute. Well, the question is to determine what is the current enclosed by this path, right? So these are the distributed currents. So when I calculate circulation of the fields, G de sigma, right? So in this case, it's going to reduce to an integral only on the surface of the current density times the normal, right? The normal that is out to the screen. So it's on the x direction, and the crossed segment, which is dy. So it's going to reduce the whole integral. So let me again, right? Just the whole integral is across the surface here. That's what J is. Right? That's the whole area of integration. Area is here, this one here. But the result is going to be 0 everywhere, unless on the small, very thin surface. So on that surface, the cross section, I could do something like this. Cross section is something like this. There's the thickness here, which is very small. So it would be JT times dy dot product with AX, JT is the current density, surface current density, K. So it's going to end up as being something like this, K dot dyx and K equals to K0 AX. So this is going to be K0 integral from Y1 to Y2, right? K0 Y2 minus A1. That's the right hand of Ampere's circuital law. So let's transport this to the next page. I'm going to cut here and put here. Right there, right? So the other thing is the field. We know that the field at this point here. So let's call this the z coordinates. So we have the integral. Let's call the path 1 and path 2. Along the path 1 of h of minus z dl plus integral on path 2 of h of plus z dl. Okay? That's the circulation of the field. So let's transport that to the other page. So what do we have here? This is the circulation. Let me restart my engine here. It's erasing. So continuing, I had to start my engine. I lost some of my notes, but I tried to recover. I think we were somewhere like here. We were trying to look at the circulation of the field. As I mentioned, is the integral on the lower segment, h minus zdl, plus integral on the upper segment. So you see that, let me redraw here. Segment 1 is this one, segment 2 is this one, and this is y1, and this is y2. And now the only component of the L we need is the one along the y direction, the y, ay. No sign, as I mentioned before. This is minus h times ay, right? H is the field in the upper plane, upper hemisphere. So in the field in the lower hemisphere is minus h. So this one is h ay. So we're going to have a dot product between ay's, which is 1. And the integral goes like this. The first one is going to be from y1 to y2 of dy times minus h plus integral from second segment, which is from y2 to y1 dy times h. Okay, this is going to give minus h y2 minus y1 plus y1 minus y2 times h, which equals to minus 2h times y2 minus y1. So recall that the current enclosed is this one, K0, So we have the H field on the upper hemisphere. H equals to minus K0 over 2. Correct sign, right? Because above the field is on the direction opposed to AY. And below is on the same direction of AY. So it means that the H field equals to K0 over 2 minus magnitude of 0 over Z times AY. That's the result we get for Ampere's circular law. So if we look at the field, right, it's going to have this behavior. Above points to the left, below points to the right. So these are two simple examples of using Ampere's law to determine H field from an integral relation, integral equation, right? Well, so just it's important to notice if H has more than one component in general. Oops, where's my mouse? Cannot move much. So if H has more than one component, and each component, even if I have one component, but depends on more than one coordinate, it's impossible to use Ampere's law to factor H out of the integral and calculate the H field. You can use Ampere's law to obtain some general properties of the field. You have some knowledge of the field, but you don't know, you cannot calculate because you cannot extract it from the integral. Oops, is here, back. He woke up. So that's what we have to say about using Ampere's law to determine fields. Let's now go to some specific calculations using our tools, our mathematical tools. One important, interesting calculation is the vector potential due to a current loop, circular current loop. So why is this important? Because we can determine the B field if we know the vector potential. It's easy to calculate the B field of a circular current loop on the z-axis, but in general it's not very simple. We have to use those special functions that we are working in this course. Okay, so we can obtain A or B, but we can obtain either A or B directly, Biot-Savart's law. But it's nice to calculate A because A resembles the distribution. The integral expression is easier to handle. So we can calculate A first, then calculate B from A using the curl of A equation. So recall that for our volume, there's expression for A, which for line currents is going to be a line integral like this for filamental currents. So that's the example we want to look at. We already had all the quantities drawn here, okay? But let's try to define things here. This is a loop of currents I, circular with radius A, okay? And we want to determine the field at point X. And then we are going to determine the A field, the vector potential. So this is the coordinate system. X is along this direction, so you can see it better. Y is along that direction, and Z along this one. So you see that the azimuth angle is phi. AR is the versor in the radial direction, lowercase r, small r, right? So we have a vector on the loop is at point A, at point x2 prime, which is associated with the versor a little r2 prime. And the variable vector in space is x prime, associated with the radial versor AR prime, and the AR is a versor that is defines the observation points. So if you look at those this construction, we have that x2 prime equals to AR prime of cylindrical coordinates. X prime, which is this vector here, is r prime, the distance, AR prime spherical versor, right? And x is RAR. The current density, JdV, is reduced to IDL prime as before, as prescribed before. The phi is, dl is a d phi, direction of a phi. Okay? So, let's move on here. So the I'm going to use a compact notation, okay? Einstein's notation, compact notation, due to Einstein's. In some demonstration, we are going to do that. In which, if you have a sum in I of, let's say, AI is going to be represented without the sum symbol. It's going to represent like this. Every time we have a repeated index, it means a sum on the index. We know the sum, what's the range, I equals 1 to 3. Let's say that I represents the x, y, and z components, or whatever components we have, okay? So, so the vector potential has 3 components. It's going to be represented by this, right? If you look at the configuration, we don't have to do that, but we can save some time by knowing what are the components of H. Well, just recall that a given current distribution that points like this, IDL, produces a that is parallel to it. That's the main principle. Any component of the distribution is going to produce differential A, which is on the same direction of that component. So, if you look at those two here, this contribution, if we want to measure the contribution of those elements on this point, again, the things depends on the distance, right? So this component that's directed along this direction is going to give a contribution which is this one. This component that is along this direction is going to give a component which is this one. If we make the right drawing, the resulting A is going to be orthogonal to this line. So that means that A has only components along the azimuthal versor. Okay? So in fact, A, by this construction, is just one component, A phi. Well, the dependence obviously this loop has symmetry for rotations in phi. So we have a potential vector that has a phi component, but that component doesn't depend on phi. Okay, so in spherical coordinates, this would be a phi of r theta phi, but because of the symmetry, there's no phi dependence, so a phi depends only on r and theta, right? So it means that I can calculate the potential vector anywhere for any azimuthal angle. Specifically, I can calculate in this point here on the x-axis, right? Just need to obtain this one. So I'm going to calculate ay at phi equals 0. Okay, so let's look at the expression for the potential vector. Potential vector equals to integral that's the expression, right? And the L prime, as we saw, equals to a phi a phi. So we only need to integrate the component that's going to give the resulting a component. So recall that a phi prime equals minus sine phi prime ax plus cosine phi prime ay. Well, on the x-axis, the only component that's going to be needed is the y component of the potential vector, right? So the y component is that due to the contribution of the L prime along the y direction, which is the cosine phi. So ay equals to integral. I can already put the limits of integral. Mu 0 I over 4 pi, integral from 0 to 2 pi. I can put this a outside also. So cosine phi d phi divided by x minus x prime. In fact, in our notation, this element here is not x prime, right? The location of the element is x2 prime. So the integral is x minus x2 prime, which is the location of the variable vector that I define as x2 prime. X prime is somewhere in 3D space, and x2 prime is on the loop. So that's the type of integral you have to calculate, which doesn't seem very simple, right? So let's just notice that x2 prime, we're going to use some expansions here. So x2 prime, so this is our loop. Make it like this. Yeah, something like that. So x2 prime is equals to that's this vector here. X2 prime equals to a. So look at the versor, variable versor ar prime, okay? A r prime but calculated at what angle? Well, theta prime, which is this angle here, equals to pi over 2 and arbitrary phi prime. So x2 prime is given by this vector here. Okay? So it's important to do that because we are going to use some expansion here. And let me get this expression. Put to the other page. So that's what we have to calculate. So recalling that x2 prime equals to AR prime for theta prime equals to pi over 2 and phi prime between 0 and 2 pi. So to calculate the integral, use the expansion, the addition theorem of spherical harmonics. This equals to sum 4 pi. Sum from L equals 0 to infinity, sum from M equals to minus L to L of 1 divided by 2L plus 1. Then we have R smaller raised to the L power, R larger raised to L plus 1. Then we have YLM. So that's the general expression, right? YLM conjugates theta prime phi prime, YLM theta phi. In the present case, X is a position in space, RAR, and X prime is equals to X2 primes. As I mentioned, equals to R, AR, at theta prime equals to pi over 2 and phi arbitrary. So what does it mean? YLM conjugate of theta prime phi prime equals to YLM conjugate of pi over 2 phi prime in this expansion. Right? So we have that those considerations. So we have these results. The expansion of the inverse function, right, is going to be this expansion with YLM conjugate calculated at pi over 2. So if you plug that into the integral, we have this whole set of terms. In the integral, this comes out of the integral, right? Everything goes out of the integral. This is inside of the integral. So everything that doesn't depend on phi goes out of the integral. So we have this YLM conjugate of theta equals pi over 2 phi prime times cosine of phi. So recalling that this number is real, so we can simply pick the real part of this thing here. I mean, this equals to is the same as the real part of cosine phi. So we use a real of exponential j phi prime, which gives cosine phi. So we can transform this integral. I mean, you can recall that YLM is complex. So in fact, we have to be careful. So we have to be careful here to pick up the whole thing, which is complex, which is from here. is real of simply real part of this replaced by exponential of j phi prime. It's the same result, right? So we have this result here. So we have what we have to do is to calculate this integral. You see that it's not that difficult. We are going to use some properties of the representation of the spherical harmonics in terms of associated Legendre polynomials. So YLM equals to this, right? YLM conjugate at pi over 2 explicitly, you see that this is a 0 here, okay? That's why we don't have no phi dependence. Different color here. No phi dependence. On the other hand, in this case, theta prime equals to pi over 2. So we have cosine of pi over 2 here equals 0. So we have associated Legendre polynomial of 0 arguments. And then the conjugate gives me a exponential minus jm phi prime. Okay? So the integral itself is this integral here. Notice that integral in phi is going to involve the orthogonal functions. This is one of them. And the other one is this one here. So we put everything outside of the integral. And we have this result here, right? So this is only non-zero if m equals to 1. When m equals to 1, this is 2 pi. So it's going to be 2 pi delta m1. Delta is the Kronecker delta, right? Just recall. Delta m1 equals to 1 for m equals to 1 and 0 otherwise. Right? So the result that we have is here, right? The integral, we're going to have the terms that were factored out of the integral times 2 pi and m equals to 1 right there. Okay? So we have only one term, m equals 1, in the sum from minus L to L, only m equals 1 is going to appear. So the result of the integral is this result here. So just noticing, associated Legendre polynomials, polynomial of L equals 1, m equals 1, and for the same reason, m equals 1 in this function here. Okay? So that's the final result for arbitrary values of the distance r and angle theta. Let's do some, let's express a little more detail this result. We have this generalized Rodriguez formula to calculate associated Legendre polynomials from Legendre polynomials. Right, this one here. So for m equals 1, you have minus 1 minus x squared to 1/2 root square. And first derivative of PL. For that one, we use a recurrence relation that is available for the Legendre polynomials. Okay. And recall that we want to calculate the derivative. We want to calculate PL1 for x equals to 0. Okay? So we have to recall that when you calculate things here. So dPL dx is given by this. Then you're going to make x equals 0. Well, x equals 0, this thing disappears. We're going to have minus here. And x equals 0 here is going to give minus 1. So this is going to be 1. So result is LPL minus 1 of 0. And we already know an expression for the P of 0, which only exists for an even number in the even index. That's the general expression, right? And this thing here, just notice that this is a factorial. Let me just see if this is right. 2n factorial. Let's see here. Well, 2n factorial. Let me just check that is correct, okay? 2n factorial equals to 1 times 2 times 4 times 8. Is this right? No. Yeah. Times until 2n. So we have 2n terms. Yeah, don't have to worry about how many terms, but just it's 1 times 2 to the first, 2 to the second, 2 to the third, no, it's not, that's not right. To 2n. Not sure this is correct. Oh, this is not right, yeah. Let me fix it here. This is not like this. I have to jump by 2, okay? 2n factorial has to be 2 times 4 times 6 times 8 times 10 times etc. times the last number is 2n. Okay? So it's going to be 1 times 2 times 3 times 4 times 5 times etc. times 2n times 2, right? 2, that's correct. So it's like this, 1 times 2, yeah. I'm sorry, this is wrong, times n times 2, so this is correct. So it's n factorial times 2 raised to the nth power. It's correct. So just checking that formula. So the 2n factorial is 2n 2 raised to the nth power times n. This one here is something like this. 2n minus 1 factorial is 1 times 3 times 5 times etc. to 2n minus 1. Jumping by 2. Okay. So because we only have the even for an odd index here, the P of 0 equals 0, For even, it's going to be like this. So PL plus 1, L equals 2N, right? Must be even, otherwise it's 0. 2N plus 1, P2N plus 1 of 1 of 0, the associated Legendre polynomial is going to be L, which equals to 2N plus 1, times P2N, which equals to, just trying to, oh, it's right there, it's right here, it's not this one here, it's here. PL1 of 0 equals to minus L, PL minus 1 of 0. Yeah, because there's a missing sign somewhere here. Just a second. Oh, okay. The PL1 of 0 is minus the derivative. Okay? Minus the derivative. And the derivative is plus here. So PL1 of 0 equals to minus LPL minus 1 of 0. So it means that the sign is correct here. So the sign is correct here, okay? So the 2 to the n is this term here. N factorial, 2n minus 1 factorial factorial. Then we have the final, loss of terms formula. It depends like this, P2n plus 1 of 1 cosine theta. Let's define magnetic moment, dipole moment. We are going to see that the general definition results in this parameter here. So we are going to define, we have to be careful with, with the variable names, I'm using M for magnetic moments, magnetic dipole moments. Sometimes you use M for a discrete variable. So let's make sure you understand the difference. At this point, I'm going to use M, which is magnetic dipole moment, is going to be right there. If we see where it came from, well, M equals to I times the area of the loop, I pi a square. It came from the formula, original formula here. Let's see what is it. Well, it came from a combination. I think there's some missing things here. Let me see here. Just a second. There's a missing 4 pi here. I think, well, no, it's not missing, because this 4 pi cancels the 4 pi on the denominator of AY. And we have a pi that comes from the integral, let me see here. Yeah, there's a 2 pi there. Then we have this, we can do this, this term here equals to mu 0 IA over 2 equals to mu 0 I pi a square over 2 pi a. So it's going to be mu 0 m divided by 2 pi a, with m defined by the product between current and the area of the loop. Okay? So there's another factor of 2 that comes out. So that's why we have this m coming in here and a down here. We have an additional factor of 2 that I'm sure I think this is right. This is not wrong, okay? We have to see where it came from. Let me just do this calculation quickly here. Yeah. If we plug that in the formula, let me do it separately here. Just make sure that we have the right factor here. The formula that we had was I'm going to write here AY equals to mu 0 IA over 2. There was a 2 before, okay? The sum that's what we have to do. R smaller to L, R larger to L plus 1, PL1 cosine theta times PL1 of 0, okay? So PL1 of 0 we just derived. In fact, it's P2N plus 1 of 0 the result we obtained was minus, right? Yeah. Minus 2n plus 1 minus 1/2 to the nth power. 2n minus 1 factorial divided by n factorial. Then I'm going to use this thing here. I'm going to make it without being careful here. Copy, paste. So let's use L equals to 2n. L equals to 2n plus 1. So you're going to have here 2n plus 1. It's going to be 2n factorial. In the denominator, 2n plus 2 factorial. You're gonna have 2n plus 2 here. 2n plus 1, sorry. 2n plus 1. And here, 2n plus 2. Then we have 2n plus 1, 2n plus 1, right? The p2n plus 1 of 0 is here. So let's try to put that. Before we do that, this is this ratio here is equals to n factorial divided by 2n plus 2 factorial equals to 1 times etc. times 2n divided by 1 times 2n, 2n plus 1, 2n plus 2, right, equals to 1 divided by 2n plus 1, 2n plus 2, which is equal to 1 over 2 times 1 over n plus 1, 1 over 2n plus 1. Why do we do that? Because we are going to cancel this 2n plus 1 with this one here. We are going to have this 1/2, additional 1/2 That's why we're going to have a 4 here in the formula, right? In this formula here, we're going to have the 4 coming out, right? What else? Then you're going to have an n factorial times n plus 1 is going to be this term here, n plus 1 factorial, right? So just checking that everything is correct, okay? So that's what we get. So the final result is this one here. This is correct. Just make sure that all the numbers are right. This is the final result for the phi component, which is the same as the AY component, because it doesn't depend on phi. If I go to another x, it would be the same result. That's the vector potential. That's as far as we can go here. There's I mean, not exactly an expansion, right? We have to truncate. Every time we truncate, we lose some information, right? So in the asymptotic regime, we want to consider what happens either if we are close to the center or when we are very far. I mean, if we are on a sphere around the center, which the distance is much smaller than a, or at a distance much larger than a. In both cases, r smaller over r larger is much smaller than 1. Okay. So we can retain only the first term, for instance, to see what happens. So that's what we want to do, right? Equivalently, when this ratio is much smaller than 1, so we're going to use only the first term, n equals 0, which is an odd index, in fact. N equals 0 gives an odd term. The index of the Legendre polynomials is odd. So we have only one term, right? Let's look at it. Let's take a look here. Not this one. This one here. Let's see. For n equals 0, what happens? Let's pick the formula. Let's calculate it. Let's pick this one. Let's make sure that everything is right. So for n equals 0, this goes out. This is 1. This is going to be 1. Right? This also is going to be 1. Factorial for minus 1 equals to 1. So you're going to have no sum. Then we have, this is what is left. Let's delete that. So we're going to have, just put r smaller to the first power, r larger to the second power. P11 of cosine theta. This in fact is a phi, right? Or a. Can put like this: a equals 2 times a phi. And this, the associated Legendre polynomial of 1 equals to minus sine of theta. So that's what we have, right? I'll raise this thing here. So A equals to this result here. Sine theta A phi. Notice that if we define a vector, which is the magnetic dipole moment m having the magnitude, which is current times area in the z direction. We're going to see why this happens, right? But let's define that. So we have m sine theta a phi is simply the cross product between m and the direct reversor ar. M cross ar is in the direction a phi and is proportional to the sine of theta. So this is equals to m cross ar. So in other words, the lowest order term is going to be mu 0 m cross ar over 4 pi a r smaller over r larger square. Okay, that's the result. So if we have I mean, for r near the origin, we have r smaller over r larger square equals to a over r square. I'm sorry, the other way. Equals to r over a square. In other words, vector potential goes linearly, right? With the distance, right? That's how it is. It goes linearly at the z-axis. On the z-axis, potential vector is going to be 0. Because it's synchroreferential lines, that become 0 on the z-axis. For r much larger than a, you have r smaller over r larger square equals to a over r square, and the potential vector is going to be then we're going to have a cancels out with that a, right? So you're going to have a square, inverse square law for the potential vector. Asymptotic behavior far away from the loop is 1 over the square of the distance. And this has to be compared with the potential of the electric dipole, right? Which is a different nature, which is a dot product. Here is a vector product. But I mean, the quantity is here, the electric dipole P dot AR over 4 pi epsilon 0 R square. Same inverse square law, right? Dipoles, the effect of a dipole on the potential is to vanish as the inverse of the square of the distance. So that's the result we get. Let's calculate the B field in the asymptotic regime. Right? Let's do this calculation. Curl of A. Okay. So it's going to be the curl of divided by 4 pi a r smaller to a larger square, right? So let's do explicitly AR, let's write knob operator DDR plus A theta over R dd theta plus A phi over R sine theta dd phi, cross product with this, I can put the mu 0 over 4 pi a here, cross product with m AR so derivative in R goes directly to this factor here. Derivative in theta goes only to this term here, which might depend on theta. Derivative in phi goes to this term at the most. Okay? So this is going to be mu 0 over 4 pi a AR cross m cross AR DDR. Now it's going to be a total derivative first term, right? Plus R smaller divided by R larger square A theta cross dd theta of m cross A theta plus same thing, R smaller over R larger, or R larger square sine theta dd phi. Right? And those derivatives are well known. M's constant goes out of the derivative. M's constant. This is going to be M cross derivative of A theta, the theta, equals to minus AR, right? I'm sorry, I'm talking about the. I'm just mixing things here. This is AR here. I'm sorry, this is correct. This is A theta. And this is AR here. I'm M cross AR. M cross AR everywhere. Okay? So the first term, this is going to be derivative of AR relative to theta equals to A theta. And derivative of AR relative to phi is sine theta A phi. So it's going to be, this term is going to be this, and this term here is going to be R smaller over R larger square, M cross A phi, right? So when we do all that, we're going to have something like this. It's kind of messy, but it's right here. That's what we were doing. We're doing this calculation here. Okay, so you're going to have AR cross M cross AR, derivative of this thing here, plus A theta, derivative of this thing here, plus A phi cross derivative of this term here. Okay, that's what you're doing. So now notice this thing here. Every time I can use this property. Let me just show you. The triple product has this property, right? I can expand ACB minus ABC. So when I have something like this, M cross AR, it's going to be M with AR M, right? Minus M dot M AR. I think this is wrong here. ACB minus ACB. Yeah. So it's gonna be my mouse right there. Here. So it's gonna be AC is this term here minus MMAR. Is this right? Oh, I'm sorry. No, it's not M. I'm sorry. Let me just fix it. Because to AR cross, I have several terms like this. I have AR cross M cross AR. I have A theta cross M M cross A theta. And I have A phi cross M cross A phi. So I have these things here, right? So let's do one of them. So it's going to be AR with AR is 1, it's M times B, which is M, minus M AR AR, right? Same thing for the other ones. We're going to have AR, A theta, and A phi. We're going to have things like this is going to appear. So just make sure that we understand that. So this is the calculation. We can pass that, right? We follow the notes. There's some calculation you can do it. Well, derivative of this factor here, which is what we need to calculate for the radial component that we are doing, we have this derivative here. R small over R large square depends well, if we consider R small is going to be A. I'm sorry, R small is going to be R. R large is going to be A, so it's the derivative of R, which is 1 over A squared. So then if we do that, to calculate the B field close to the z-axis. I mean, this is easier to calculate directly by Biot's law on the z-axis to calculate the same results. It's proportional, same direction as the magnetic dipole direction, right? Z direction. So you see that the loop on the center makes a field like this. In fact, the field in z-axis is always on the z direction, right? So the current loop does a field like this. That's right. So for a large R, then the derivative on R has to be calculated. R small is going to be A, R large is going to be R. Then the derivative is going to be the derivative of R A over R squared equals to minus 2A over R cubed. If we play with the things, we obtain, let me just That's what we get, okay? We have radial term is going to be this. The dependence is going to be 1 over r cubed for the field. Then we have these terms, right? We're going to have here 2m dot ar, which is minus with minus. Minus 2m cancels with those factors here. So it can make this equals to 3 if we subtract the same term, okay? Minus m equal dot ar. That's what we do. So we're going to have a 3m ar. And the one that's negative, we combine with the remaining terms here. M a theta, M a phi, and M a r. They together combine to give the composition of M in spherical coordinates, which is this term here. So the result we get is this one. The B field is given by this result. So this is the same expression for the E field of a for an electric dipole. So it has the classical representation 3m dot ar minus m, dependence 1 over r cubed. Okay. So that's what we have. Also, it's important to notice, I mean, if we want to determine what is the B field dependence on R for a small r, we just determine the first approximation, we would have to retain the next lowest order mode term in the expansion of A. So we have to go to n equals 1 to really see what's the dependence of the B fields and the components close to the origin. Okay. So now that we have done the calculation, let's move to the next topic of our lecture. Let's determine now, there's another typo here, this dipole. So let's consider when you have a localized distribution, we are going to now really define what is the magnetic dipole, what is magnetization. So we are going to assume that we have a distribution of currents, okay, which is enclosed by a sphere, let's say, of radius r0. All the distribution is located in that. So we can determine the asymptotic behavior of the B field of this distribution far away. So we want to look into molecules, atoms, sets of atoms and molecules far away. For instance, how a single atom, what's the contribution to the magnetic field due to a single molecule, due to a single atom. So we are going to enclose that atom or molecule or set of charges, moving charges, into a size. So we want to consider what is the behavior of the field far away. We are going to use stationary currents, right? Divergence of J equals 0. It means that the flux of J to a enclosed surface is always 0, and also that the normal component of J equals 0 on the surface. In other words, if I get this sphere, or this sphere, J normal outside J equals 0, so by boundary condition on a stationary current, the J component in the normal direction is always 0. There's no normal component, okay? So it means that in this sphere, I'm sure that Jn equals 0. So let's calculate the magnetic effect of this localized distribution. We're going to have the vector potential by that expression. Let's expand the inverse function to the lowest order. Well, right? When the x prime, magnitude of the vector x prime, is much smaller. It's much smaller than magnitude of x. So we know how to do that. Right? Let's recall f of x plus plus a small vector. Let's call delta x, small delta x, to first order equals to f of x plus the dot product between the displacement delta x with the gradient of f for delta x equals 0. Okay? So if I have, if the function is, if we say x prime equals to minus delta, in other words, delta x equals to minus x prime, we have the inverse function so this is approximately the function at delta x equals 0 right, plus delta x, which is minus x prime, dot product with the gradient of the function, which is minus x prime, divided x minus x prime cubed. Right? So on this one, that in fact is at x prime equals 0. So this is going to be equals to approx 1 over magnitude minus x prime dot x over x cubed. That's the expansion for a small size vector x prime. So that's what we have. So when you do the expansion, we have this terms. You see that's the x magnitude of x can be extracted from the integral. So you're going to have 1 over x and a term that has an integral of j. That would be the monopole term, because the potential that varies with 1 over x, 1 over the distance, is that due to a monopole. So if there is a magnetic monopole, that would be in this result here, right? And the other term is the dipole term, because it goes with 1 over the square of the distance. We have the magnitude of the distance up here, and down here we have the cubed, so we have 1 over square in this term here. So this is a dipole term, right? Because dipoles, the potential varies with the inverse of the square of the distance. So let's calculate those things. We're going to use a property to calculate those integrals, to see what they are. There are two properties we are going to use. Okay, one of them is look at this. We're going to use the fact that J is stationary, and we are going to use Gauss's theorem. Gauss's theorem relates to the divergence of a field with the normal component of that field on the surface. because J is stationary, the normal component on the surface is 0. So consider this quantity here, xi times j, right? Xi is one of the components. Let's say x1 equals x, x2 equals y, x3 equals z, right? Any component. So what is the divergence of xi times j? Chain rule is going to be j dot gradient of xi plus xi divergent of j. But j is stationary, this is 0. So this is going to be j times gradient of xi. Well, gradient of xi equals to the versor ai. So this equals to j dot ai, which equals to ji. So in other words, the ith component of j equals to the divergence of xi j. So what does it mean? If I make an integral, dv is going to be an integral of divergence of xi times j. Well, Gauss's theorem establishes that this is equals to the surface integral of xi times j. So this has the normal component, right? The sigma xi jn on the surface. And this equals to 0 because, as we mentioned, we enclose the whole surface and we have a stationary current distribution. So it means that integral of volume of ji equals 0, and the same happens to the vector, because if I sum the components, I have the vector integral of j dv equals 0. So there's the monopole term is 0, right? This term here doesn't contribute. There's no monopole, magnetic monopole, because of the nature of the current. Second factor is this term here. Let's look at the second term now. Notice that we have an integral, okay. Let me go back here. Integral of the second term involves an integral of x prime, right? Times j. You notice that this factor here, this factor here, is one piece of expansion of the cross product, which is the cross product of x cross x prime cross j. If we expand this term here, we're going to have the triple product is going to be xj x prime, right, minus x prime j, right? So in other words, the integral, the volume integral of the cross products equals to the volume integral of xj x prime minus the volume integral of x prime j. In the monopole term, in the dipole term, we have this x prime j. So we're going to try to see if there's any similarity between those two integrals here, okay? So that's what we want to look at. I'm going to look at this integral here. I'm going to just mark it 1, and this integral there, let's call it 2. We had an identity, right? Let's make a second identity. We're going to use the Gauss's theorem and the fact that J is stationary. Let's construct the vector xi xj times j. Before we constructed xi times j. Now we're going to construct xi xj times j. And let's calculate the divergence of this vector. This is equals to j cross j dot product with the gradient of xi xj plus xi xj divergence of j, which is 0, plus 0, right? So this is going to be j. So his chain rule, xi gradient of xj plus xj gradient of xi. So this is aj, this is ai. So it's going to be j dot aj xi plus j dot ai xj. Okay? So this equals to jj xi plus ji xj. Now we have this identity. So this is equals to the divergence of xi xj j. So if we make an integral, volume integral of the divergence, in the volume, right? So it's going to be the flux times xi xj. And we know that this is the normal components of j on the surface that includes all the currents is 0. So it means that the integral of this sum here is 0. So in other words, what it demonstrates is that dv this is dv, right? I forgot, yeah. So dv xi jj equals to minus dv xj ji. That's the result we get. Let's go to the next page. So let's put now in the prime variable xi prime jj equals integrals xj prime ji. Okay? So if I multiply now both members by xi, I have this result here. This is minus, right? I forgot that. Minus xi So every time we have a repeated index, it means we are summing on that index. And also we can compose all these terms to make the vector. So this is going to generate a dot product between x and x prime. And when we sum on j, multiplied by the versor aj, you're going to have the vector j. So this is going to generate, this is minor here. It's going to generate something like this. dv prime dot product of x with x prime times j, after you get all the components, equals to minus dot product of x with j x prime. So that's what we have. That's the result we have, right? So this gives this, this gives that. So what did we have before? Let's see. We have terms 1 and 2. Term 2 is xjx prime. Is term 2, right? Term 2 is this one here. Right? My mouse doesn't want to come back. Come on. And sorry. And the other term is term 1, xx prime with j is term 1, right? Term 1. So one of them is minus the other one. So the one that is the dipole term is this one here, xx prime, right? So the other term, so if you go here now, sorry, if you go here, it means that 2 equals to minus 1, so it means that this equals to minus, so this is equals to minus 1, right? So this is going to be minus 2 times x prime j. Okay? I'm going to erase this thing here because I don't need it now. So it means that the integral that appears here, integral of dv prime x prime j equals to minus half of the integral of what is it? I hope it's right. Yeah. Yeah, it's correct. Let me just erase it here. Equals to minus half the integral of x cross x prime cross j, or if you want, equals to, let me erase this thing here, erase this part here. So equals to 1/2 of the integral. I'm going to put like this, integral of dv prime. I'm going to make like this, wait, equals to 1/2 the integral of x prime cross j cross product with jx. Okay? So the term that appears in the dipole term, this term here, can be written like this one, right? So exactly what we have here. I mean, Jackson demonstrates that too, if you can see in Jackson, but that's how we did it. So is this term here between brackets cross x. This is the definition, the general definition of the magnetic dipole moment. Okay, so it has dimensions, current times area, if you see the dimension here. current times area. Okay, so when you use that, we determine the vector potential of a localized distribution with a general definition of the magnetic dipole moments. And the result we get is this one here, the same one we got using for the circular loop, right? So the definition of this quantity, the quantity that appears in the integrand, let's make it here. So the definition is m equals to integral of x prime cross j over 2. So this is called the magnetization, which we are going to be, magnetization for localized things doesn't have much meaning, but for distribution of dipoles it's going to have a meaning. But then we can have a magnetization, which is this density function here, x prime cross x j over 2, which is measured in amps per meter. Something we're going to explore, right? So as we showed before, if we have a circular loop, right, you have that the magnetic dipole equals to the moment equals to integral of dv prime x prime cross j over 2, but in this case j dv prime equals to I dl prime. So it's I over 2 integral of x cross dl prime, right? So that's the integral we have. Notice that the area of this triangle here is simply given by x cross dl prime gives the area over 2, right? Gives the area of this triangle here, right? Let's see quickly here. Any path, right? I can calculate the area by summing the triangles, right? And each triangle of this can be calculated, the area of a triangle. Let's make it here. We have an arbitrary triangle here, right? So I have a vector x. Let's call this delta L, right? So x and delta L. So let's see here. Let's make a parallelogram here quickly. So let's make a parallelogram. So we have this the area of this parallelogram equals to size of x times this perpendicular segment here, right? So if we have this angle here, theta, so this h here equals to delta L sine theta. So the area of the parallelogram equals to size of x, size of delta L sine theta. And the area of the triangle is half of that. Sine theta over 2, which is the magnitude of x cross delta L. So, in fact, the area of this figure can be calculated, right? We call this dl on this x. The area of this closed figure equals to x, the area, the vector area x cross dl integral, in fact. Sorry about that. The area is going to be the integral of x cross dl over 2. Right? So the dipole moment of a loop of arbitrary shape that makes a closed path is going to be, it's going to be the area of the loop, right? In this case, pi a square az times the currents. So m equals to, in fact, the dipole moment equals to m for a closed and planar loop equals I times the area sigma, whatever shape it has, okay? Let's continue with our last part of our lecture. Let's talk about the magnetization current and types of magnetic media. Consider that we have a volume in which you have the coexistence of free current. What is a free current, right? We have two components. Free current. By free current, we mean that current provided by electric circuits. Right? The standard circuit makes a circulation of charges, free charges that move across the circuit. This is called the free current. And we are going to represent those by the density current J. So every time we see a J symbol, it means that we have real free carriers moving across the circuit, across a region, etc. Okay? And also, we are going to have atomic currents. Okay? We have those localized carriers. Well, you might have a molecule you have in which the electrons have a state of orbital motion. Let's talk about, in classically talking about those. We are going to have an orbital motion that sets a magnetic momentum, a magnetic dipole momentum. You might have this electron spin, electron spinning, having its own magnetic momentum, and so on. So these are the type of effects that we call effects given by localized carriers. So we have those, localized current elements. It's not free charge moving with a displacement across a material or across a circuit. It's just state of magnetization, let's say, of the material medium involved. Okay, so we have one thing is the current density. The other thing is, the existence of magnetization state. What is magnetization? Magnetization is the density of dipoles per unit volume. We give an expression for magnetization equals to 1/2. In fact, magnetization is 1/2, not the integral, 1/2 of x cross J. That's the magnetization. Well, but this is let's put Jm, not Jm. Let's make a J which is a localized. Let's Ja. Let's say A as atomic or molecular current, localized. Okay, or else I can put here a localized. Okay, but we are not going to use this symbol here. We're going to use the magnetization state, which is equivalent to that. This is the momentum of the currents, but these are separated from the free carriers. Okay, so we have two things. So in a given volume, symbolically, we can have, put the volume here. We have the coexistence of free currents, JL. In fact, I should use another symbol here. Let's call it F. Okay, this is the Portuguese corresponding Portuguese translation for this. JF as free, and in addition we have the magnetization, which is localized current. So the potential due to those two contributions is going to be contribution due to free carriers, JF, okay, and due to the localized current, which is the magnetization, which gives a contribution here, which is mu0 dm cross x minus x prime. Dm by in turn is m dv prime. Okay, so this thing here is dm. So that's what you have to calculate. The potential, the vector potential is given by these two contributions. I'm going to change all the subscripts here so you can understand. JF plus, when we integrate, plus this term here. Now we are going to, you see, in the same fashion we had in the case of electrostatics, we have a denominator here which is the third power. We have a denominator here with the first power. One part of this integral we can transform in so that it has a shape very similar to this one. Let's do that. To do that, we are going to use this identity, the chain rule. Okay, let's work outside here. Also, you have that the curl of m divided by x minus x prime relative to the prime variable equals to minus m cross the gradient there's one term, and the other one plus the function curl of the vector, right? So, well, I mean, this is nabla prime. We know that nabla of the inverse function equals to minus nabla prime which is minus x prime divided by the magnitude cubed so the nabla prime, of course, is going to be plus, right? So here we have, we can replace this thing here. By x minus x prime divided by the magnitude or modulo to the third power. Then what we have? This is what we have. Let me see if it's right. We have this term here, m cross the nabla prime, right? M cross nabla prime. So m cross nabla prime So in other words, this is if I put this to the first left hand side, you're going to have a minus this factor here, minus, if I move this over here, let me erase this thing here. We're going to have something like this. That's what we have there. M cross x minus x prime magnitude to the third power equals to 1 over, let's do like this, curl of M minus curl of the whole thing, right? So we have volume integral, so we replace the volume integral by two volume integrals. One of them has the same denominator of the free current term. So when you do that, we can combine the numerator terms. We are going to have this equivalence factor in here, and in the other, we're missing some constants here. I'm sorry. My mu 0 is not here. Right, here too. So you see that one integral is going to be this integral here, volume integral of mu 0 minus, right? Have a minus there. I'm going to put all in this inside of the parenthesis. Curl of mu 0 m divided by 4 pi x minus x prime, and we know that this is that's definition of the curl, the dual definition relative to the divergence. We have dual definitions of Gauss's theorem. If you change the dot into a cross, you have the dual corresponding definition involving the curl. This is, I'm going to put on the side here, is this identity here, the volume integral of the curl of a vector. Let's call it a different name, okay? Let's say C equals to the surface integral that binds the volume of the sigma cross the vector. So this is equivalent to Gauss's theorem if we just change the dot here. We point that out on in the review of vector algebra. So what happens here is that this is going to be the surface integral of the sigma cross m. I'm going to put the mu 0 here over 4 pi x minus x prime. Okay, so let's move that to the next page. Let's do some little algebra here. So and this is if we use the sigma equals to n points outwards to the volume of the localized material. You know, you enclose everything in a volume. So there's going to be a surface integral mu 0 n cross m or if you want, you can change the sign, change the order here. Mu 0, right? Don't forget that. So we have a surface integral, same denominator, right? Recall that A for a surface current is given by surface integral, can be on a closed surface if you want. Mu 0 divided by 4 pi x minus x prime. So we have a surface of current, then your vector potential would be something like this. So it means that this is an equivalent surface current. We are going to denote by Km equals to m dot product with the that exists on the boundary of the volume. Okay, we enclose all the currents, we go to the boundary and see if we have anything like this that's not zero. So we have an equivalent surface current. This is called the magnetization. Surface current density, or if you will, surface current density of magnetization. Let me put magnetization here like this, right? So we have a surface contribution due to the magnetization, which is equivalent to a distribution of current on the surface. And in the volume, I mean, when we did that change, one term, as I told you, one term had the same denominator, and then we collapsed both terms, the free currents and the term that is the magnetization current, which is the curl of M. If you recall, one term that we did here, that appeared here, was exactly that, right? Curl of M. And we joined this one with the free current, put in a single term, so we have an equivalent current density, which is the sum of the free current density plus a term that comes from the magnetization of the material. It's as if the magnetization in the volume gave a contribution given by curl of M. So everything occurs as if you can replace your material by the free currents plus the equivalent magnetization currents and put back in the place of the material. Okay, that's the idea of these equivalent currents. Well, so let me summarize here what we have. If we have a volume, volume V, in which for some reason we have a state of free currents and magnetization. For example, we have an iron core, okay? Then we have a winding around this iron core, like this. They are not exactly on the same volume, right? They are in different regions, but you can conceptually, so this is the free current, and the magnetization state is in this material here. So that's what you have. So symbolically, we represent by a volume having those two things. Some places JF is 0, some places M equals 0. For instance, outside of this core, M equals 0. Inside of the core, JF equals 0, right? So what happens when you have this volume? Let's put it in the next page. You can replace this by an equivalent. Let me copy it. An equivalent problem outside this vacuum, okay? Vacuum here, and here's the magnetization state in this volume here, and current this. You can replace the volume in which you have to use these two quantities by a vacuum. There's nothing else here, right? Except that inside of this volume, you have an equivalent current density, effective, how did I call it? Equivalent. An equivalent current density. And here we have a magnetization current. And also if you have a free current density on the surface, you have also Kf here. So you can solve the problem as if you were in vacuum with those, distributions in the volume and on the surface. Whatever method you use to calculate the fields can be used. You can consider that you take into account all the currents in the region, replace everything by vacuum, and calculate the fields. That's the idea, right? Just 1 second. Just a second. Yeah. So the question is this: why do we have also, when we do this model, why do we have a surface current, magnetization surface current? So just recalling, in the volume we have a magnetization current given by curl of M. On the surface we would have a magnetization current density equals to M cross N, right? So where does it come from? Where does the term come from? You have two ways of calculating the integral when you have the coexistence of magnetization and free currents. Okay. Suppose you have your volume with both free currents and magnetization. Okay. Well, you can calculate the vector potential by doing this. You can you can calculate the vector potential in any point in space, integrating in the entire space. Then you are going to have this type of thing: integral of dv prime j equivalence mu 0 over 4 pi x minus x prime. In this integral, we have the entire space, the whole space, okay? That's one way to do it. But when you do that, you recall that J equivalent equals to J free plus Jm. Jm is given by this thing here. But when you're doing the whole space, you have to consider that the magnetization has a sudden change in the boundary here, okay? And you have to calculate that when you calculate Jm. I mean, the curl of M has to take into account the sudden change of the magnetization on the boundary, okay? When you do integration in whole space. Alternatively, you can do the integration on the volume only, because outside the free current is 0. On the volume, then you're going to use A equals to the equivalence mu0 for pi x minus x prime plus the surface term. So here is only on the volume. Then the integration due to the sudden change of the magnetization current on the surface is taken into account in the surface integral, in the same way that if there's a sudden change of the current J on the surface, it is going to be included here, okay? So the surface integrals would be here. If you have a free current, then you're going to have a K free. If you have magnetization current on the surface, you're going to have a Km. Right? So here, this term here is the result of the integration that was carried out here, taking into account the sudden change of both free current and free magnetization, and magnetization current. Okay, let's take a look. Let's look at the magnetization current term. Suppose that we integrate in the whole space. What happens? If we make an integral, okay, here is region 1 where we have magnetization. Here is region 2 where you don't have magnetization. You are integrate the volume where you have the magnetization current in the whole space. What happens when you do the integral? Your integral goes up to the volume, to the boundary of the volume. Then you stop and you calculate what happens on the surface, right? Well, let's see the integration across the surface. It's this integral here. We're going to have a small closed surface, closed volume, that's going to give the contribution of that small area, okay? Due to the volume integration. Well, again, if I use that integral theorem, this is going to be the sigma cross m, okay, which is this term here, which is the JMdV, okay. So JMdV is exactly that. Let's calculate that integration. If you calculate m on the outside minus m in the inside. M outside is 0. M inside of the volume is m. As the height of the cylinder goes to 0, so this is a boundary condition, right? When the height of the cylinder goes to 0, what's going to happen? You're going to have a volume current times h, which has a limit, which is a surface current density times delta sigma. Outside, m, this is m2. This is m on the outside. This is m on the inside. So outside magnetization is 0, inside is m. So what's going to happen? When you do the volume integration, the result, consider that you have this limit here, Jmh equals Km. Then the result is that the volume integral, the term that is relevant in the volume integral is m cross n, which is the surface current density or magnetization current density on the surface. Okay? So using or not using the surface term is a matter of how you integrate. In general, we separate integrals. You don't integrate in the entire space, because if we do that, we have to take into account sudden changes of the functions on boundaries. What we do is to integrate in the region of existence of the quantity, which is the current density, and at the surface, the contribution to the surface is the surface term that we showed in the integral expression we just showed to you, okay? So that's the what happened. Magnetization is a function that might be constant, for instance, in the volume, but it's going to be zero outside. So there's going to be some change in the boundary. So that's the change that's equivalent to the volume integral that yields a surface integral. That's why we have a surface term. Okay. Let's make some examples on how. So you can have some feeling on what is a magnetization current. Let's say you have this plate, circular plate with this finite thickness h, right? And suppose that this is a magnetic plate, circular plate, in which we magnetize uniformly in the entire plate along the vertical direction. Let's say that this is the z direction, okay? Another color there. Z direction. So m is constant in the plate. So it means that the volume density magnetization current in the volume, which is the derivative here, essentially, is zero because m is constant. And the only thing that we are left with is the contributions on the surface. Let's find the magnetization currents. So we have the normal to the top surface, top hat. The bottom, the normal goes down, and the lateral surface of this plate, which has a height h, which has a normal direction n, which is the radial direction in cylindrical coordinates. So let's calculate Km in those three surfaces. In the superior surface, the upper surface, M and N are parallel, so cross product 0. The same thing in the lower surface. So you don't have any magnetization current on the top surface and on the bottom surface. All you have is on the side surface, lateral surface, in which you have a radial direction versor normal to the surface. So AZ cross AR equals to A phi. So that's the current. M0 amps per meter, dimension of surface current, right? The total current that circulates on the side is simply you calculate every time you cross a segment, surface current. Let's make like this. Let's put like that, okay? That's the normal to the segment. You are crossing this segment here, the L. So the current density is moving somewhere here. Let's say suppose that your current density is a surface current like this, given by K. So the amount of current that crosses the segment is di equals to K dot N dl. And the total current between A and B is the line integral, right? IAB equals to line integral over this path. Let's call it CAB of K and dl. That's how you calculate given the surface current. So in this case, we have a lateral, surface. We have a current density which is K equals Km, right? M0 A phi. So the segment that we are crossing is this one here, AB. And the height is h, right? So the normal to the segment is A phi. So the current IAB, as we just demonstrated, just review it, is integral from Z minus h over 2 to z plus h over 2. The L is the z, right? dz a phi dot m0 a phi. Result is going to be m0 times h. Amperes. No, we don't have accent here. Amperes, okay? Amps. Amperes per meter times meter, that's ampere. So, what is this little circular plate? Well, what happened here? I mean, the collective effect of all the localized, microscopic currents, they cancel the effect in the bulk of the material, but we had some residue of the effect on the border of the material. So that's what happens. You see, you have several microcircuits like this, and in fact, in each of those straight segments, you have a canceling of currents, right? And the net effect is some current macroscopically existing outside. So that's what it is. Okay? That's what we have. It's like a magnetic dipole. So this plate is like this. That's what the magnetic needle is, right? Magnetic needle, let's make it a cylindrical. We have several, So the magnetic needle, if you assume it's cylindrical, okay, even if it has a tip like this, but you're going to have equivalently a surface current density, a giant dipole, in which you have a current that circulates on the wall of the cylinder, and that gives a magnetic dipole like this. If you apply a field, the tendency, we didn't show that, right? But the tendency of a dipole is to align along the field. That's why the magnetic needle goes along the field, right? So there's the same effect. You have a cylinder, like a needle, then you have that effect. You can have other shapes. It's going to be magnetic, but it's going to be the effect of it's as if we had a macroscopic current, but notice there's no carriers moving around, it's just a collective effect that gives that impression of a macroscopic current, okay? Let's calculate, let's show how those concepts of equivalent current density are interesting and important, and they facilitate sometimes the calculation of the fields. For instance, suppose that you have a magnetized sphere, okay, uniformly magnetized, with the magnetization along the z direction. Let's calculate the field because it's simple to calculate at x equals 0. Okay. So let's use, what we're going to do? We're going to replace the sphere by the equivalent currents. In this problem, there's no free current density. Only magnetization, right? So it's the magnetic effect due to the material medium itself. So the B field by Biot-Savart is going to be, in this case, constant magnetization means that Jm equals 0, and Km is different than 0. Km equals to m cross n, right? So the field can be calculated using Biot-Savart's law, Km cross x minus x prime divided by x minus x prime cubed. You can make x equals 0, x prime is a point on the sphere, which is AR prime. Then, if you plug that, you're going to have the area is a squared the omega. Let's see here for the sphere. You have at a given point okay, you have that's in this point here the normal AR prime. Okay, this is theta prime. At this point, magnetization, if I put it outside like this, just to draw the vector, so Km equals to M0 AZ cross AR prime, which is equal to M0 sine of theta prime AZ cross AR equals to A phi. Right? So this sphere, this magnetized sphere, is equivalent to several loops piled up one on top of the other with varying radii. So we have, I'm going to draw like that, in vacuum. So we replace the sphere, put instead those current distributions on the surface, and make it vacuum. So that's what I have, several loops, several disks, if you want. So we replace the sphere by those equivalent current loops, right? I'll pack it together. And you replace that, so you're going to have here vacuum outside, vacuum inside. Vacuum plus Km observe that the current is circumferential, and if you look at the current, it's going to be like this. I mean, 0 in the North Pole, you go from 0 to pi, right? Theta goes from 0 to pi. So maximum in the equator and 0 in the South Pole. Pi. Right? The peak current density is here. Then it goes increasing again until it vanishes in the South Pole. The North Pole and the South Pole. So that's what we have. Right? So calculating the field, just use this current distribution in vacuum. So Biot-Savart's law is very easy to calculate. That's why we are using here the permeability equals to mu0. So this is, you have a squared times a is a cubed divided by a cubed, cancel. So I have an integral to be calculated here. I'll leave it to you, okay? This is easy. So when you do that, we calculate that the field is 2/3 of mu0m. And this is valid not only in the origin, but anywhere inside of the sphere. It's the same as the dielectric sphere with polarized material. the field is uniform inside. And outside is due to a, is exactly due to a dipole. I think we are going to calculate that exactly. So, okay. Now we are going to arrive at Maxwell's equations for magnetostatics in any material media. And together with that, we are going to derive the constitutive relation. Okay, let's get back to the current density, the volume current density, which is the one that has importance in the differential equations. We know that integrating the volume across the surface, we find the surface current density of magnetization. So we don't have to worry about it, because surface currents, they arise due to integration processes. So in differential equation, you only look at those volume densities. Current density, charge density, everything is volume, right? So what did we say? See, we showed that the coexistence of material media and free current gives an equivalent current density composed by a free current JF plus the magnetization current JM, right? And the magnetization current is given by curl of M. Let's look back at the Maxwell's equations. Maxwell's equations, we go back to the original field, which is B field. H field was defined temporarily, but let's forget H field now. Now we only have one field, which is B field. B field takes into account all the types of currents around. So it means that curl of B equals to mu0 times the total current density, which is J equivalent, and which is going to be broken in two components: the free JF plus the magnetization, is curl of M. Now we can combine those two curls, this one and this one, together into a single term. And on the right side, they're going to have, right-hand side, they're going to have the free current density. So to eliminate this parameter mu0 here, we are going to redefine this vector B minus mu0m. We are going to call it mu0h. Okay, so we're going to do this. What we have is this. Curl of B minus mu0m equals to mu0j free. We are going to redefine this as a new vector, which is going to be, we want to eliminate the constant here. So this B minus mu0m, you are going to call equals to mu0h. And now is the final definition for the H field, the magnetic field. We did a temporal definition. In the absence of M, B was equals to, for M equals 0, B was mu0h. With the presence of magnetization, that's the relation we get. And this is going to be written like this. So B and H are related by this constitutive relation for the magnetism, which depend on the nature of the material, right? Different materials have different behaviors. So we have that. When we do that, and plug in here, we have the second equation for the magnetostatics, which is curl of H equals to the free current density. From now on, we are going to drop this index. This is going to be called J, and it's implicit that every time we have H in the equation, in Maxwell's equation, the right-hand side means free current. So current due to free carriers. What are free carriers? Well, free carriers are ions, positive or negative, in an ionized gas. Free carriers are ionic species in a solution, in an ionic solution, in a battery, for instance. They can be electrons and holes in semiconductors, or simply electrons in conductors. These free electrons, right? This is free carriers. So every time we have an H on Maxwell's equation, this is free current. It doesn't take, this doesn't have any part of it that has magnetization current. Okay? So now we have Maxwell's equations. Magnetostatics, right, is represented by divergence of B equals 0 and curl of H equals free current density. We are not going to use subscript anymore. And constitutive relation, which depend on the nature of the medium. Okay? So that's what we have to summarize Maxwell's equation for magnetostatics. Right? We can also, we have integral relations relative to those, which are obtained by the well-known integral theorems. Magnetic flux outwards or inwards of any volume and enclosed by a surface sigma equals 0. There's no magnetic charge. And the Ampère circuital law, which is the same. HDL equals to the current involved by C. The sigma. These are the two integral laws that we get. Okay. In addition, we have to pay attention to boundary conditions that we have to use. Sometimes we have different material media, different regions. Then we have to know how to connect fields across the boundary. So let's look into that. This is a boundary. We have to read two different media, medium 1 and 2. Let's represent the fields on medium 1 equals to H1 and B1, medium 2, H2 and B2. You'll notice that the fields vary in the media, but they have some limiting value on the surface. So the question is, how do we connect those fields? What are their connections? So we're going to use differential cylinder with a height that goes to 0 and a surface that is very small, is differential surface. We are going to use, instead of the traditional integral equations, let's go back to the differential form. This gives this integral connection, right? Magnetic flux outwards or inwards any closed surface equals to 0. The other equation is this one. Now I can integrate in the volume and obtain another integral equation. It is not Ampere's law. It's this one here. And then we can use this relationship, use that integral theorem, volume integral of curl of H equals to the surface integral of the sigma cross H. So we can have also this different integral here, okay? Sigma is the surface that limits V. So we're going to use those two equations, surface integral of the sigma b equals to 0, surface integral of the sigma cross h equals to volume integral of j. Let's apply that to the cylinder here. That's the one we just described to you. So let's go to this one. Equation I. Gauss's law for magnetic flux density. When you make the surface go to 0, the integral has a component on the lateral surface of the cylinder, one component on the top surface, one component on the lower surface. When h goes to 0, because b cannot be localized, b spreads over a volume. So when the area goes to 0, the lateral area goes to 0, so the contribution on the lateral surface is 0. And then we have B2. So the result of this integral here equals B on the upper part times n, which is the normal that goes from 1 to 2, which is this one here, times the area, that's the flux, because the area is differential, minus, because here, the normal here is downwards, so it's minus B1 n delta sigma equals 0. Conclusion, you have n scalar dot product, right? Scalar product B2 minus B1 equals 0, or B normal is continuous. So whatever happens, if you make a plot, that's the boundary, region 1 and 2. Whatever behavior you have on each side for the B normal coordinates, if you plot that against, if you go to the boundary, then you make a plot, so B has to connect continuously, So B changes, that's B1, that's B2, but they connect continuously on the surface. It's a continuous function. We don't say anything about the derivative of B, but the B itself is a continuous function. There can be no jumps on the surface, right? If you go now for this equation here, the second equation is this one. This one here. Apply that to the cylinder of height equals to h, base equals to sigma. So the integral on the side surface also is going to be 0. And on the top is going to be n delta sigma cross h2, right, in the top surface, which is medium 2. On the bottom surface is going to be minus n delta sigma cross h1. So that's the contributions to h in this integral. So we're going to have here delta sigma, right, which is already being cancelled out. And in the volume, that's the result of the integral. The volume integral of j is j times the height times the lateral area. Well, if there's a limit for this, that's going to be the current density, free current density on the surface. It's going to be K. That's what we talk about when we make volume integration, right? We pass through the surface and we get a K if there's a K current density on the surface current density, right? So you have K, this sigma here. That's the result. And you cancel that, you obtain this boundary condition, right? So there's a discontinuity in the tangential component of the field. And if you have that, that's because you have a current density. So let's explore a little more here. So if H2 minus H1 is not parallel to n, it's because we have a current density on the surface. In many cases, K equals to 0, then you have n cross H2 minus H1 equals to 0. So H2 minus H1 is parallel to n, right? So that's what it is. I mean, you have n, normal direction. You have to make a difference between vectors so that the difference lies in such a way that the difference is going to be parallel to the normal. So it means that both vectors have the same tangential component. H tangential 2 equals to H tangential 1. That's the meaning when you don't have a current density. That's the boundary condition. H tangential is going to be a continuous function. Otherwise, you have to use this equation here. Okay? So to conclude the lecture, I'm just going to talk about very briefly on types of material media because there's such a vast science behind the fundamental properties of magnetic materials. We are not going to do that in the single page of a lecture, okay? We're just going to do very superficial here because if we need to understand, we have to go to the, to the several references on magnetic properties of materials. So just to be very brief, in summary, okay, that we talked about that before relative to polarizable media, dielectric materials. Now, relative to magnetic materials, have different types of material. Have linear materials, you have linear media. They can be paramagnetic or diamagnetic, for instance. And you have non-linear media, which are the ferromagnetic or ferromagnetic materials. Okay. So how do you define that? I mean, the media have curve, magnetization curve, apply a field, a magnetization curve. You can have saturation if you have a strong coupling between dipoles in the material, and when we remove that, we might have hysteresis effect, as we described before. Some materials, ferromagnetic materials, they have hysteresis effect. So you saturate, right? Because the dipoles might be randomly aligned, but they couple together. They also interact very strongly. When you apply a field, they all align. And when you remove the field, the fact is that they remain aligned. So at zero field, you still have a result here different from zero. So you might have this type of effect, a hysteresis curve, in which you don't know, given H, you don't know what's the value of M. You have three solutions here, right? So it depends on the history. How did it arrive at that state? Then you might determine what's the magnetization. So these are nonlinear material. You have paramagnetic material in which the collective effect is such that the magnetization goes in the same sense as the applied field. So we have a curve that is linear like this, paramagnetic, right? In which the magnetization increases as a function of the applied field. Normally, if you I mean, based on Faraday's law, on Lenz's law, when you apply the field in material, it tries to make a reaction field, so that the induced dipole moment is against the field, the other way. So materials like this exist, and these are the diamagnetic materials. Every material, when you apply a field, tries to react so as to produce a dipole moment that goes against the field. But there are other effects that dominate. That's why you have materials maybe paramagnetic or ferromagnetic. Other effects you have called internal effects that are dominant. But in certain or other certain materials, you have a very small, remain diamagnetic response. So for linear material, for linear media, M and H have the same physical dimensions. Magnetization, Ampère per meter, H field 2. So for linear media, we have what's called the magnetic susceptibility, a dimensional parameter. And if the susceptibility is larger than 0, we have a paramagnetic material. And if negative, you have a diamagnetic, right? In general, these numbers are very small. The chi-m is very small, either for para or diamagnetic, but they are not 0. So what happens? Let's assume that the medium is isotropic, so I'm not using vectors here, I'm using just a scalar connection. So B equals to mu0 H plus M, which is chi-mh, which is mu0 1 plus chi-m times H. So for all effects for linear media, either paramagnetic or diamagnetic, B is going to be one plus chi-m, and this is the permeability of the material. Mu equals mu0 1 plus chi-m. So what happens for paramagnetic material? We have mu over mu0, the relative permeability, larger than 1. And for diamagnetic material, mu over mu0 is less than 1. Okay? So, and for linear media, it's very, very simple to do calculations. All the formulas, if you enclose your free current by a permeable material, having a permeability equals mu, you only replace mu0 by mu in the expressions, okay? For instance, let's assume this problem here, okay? You have a current, then you have a cap made of permeable material with the permeability equals to mu. Let's say that in this region here, let's say up to radius equals to A, we have a cap, cylindrical cap, cover, having a permeability μ. Outside permeability is that of vacuum. So everything remains valid. If you calculate by Ampère's law, you're going to see that the field inside is going to be, the B field is going to be mu times I. And outside is going to be mu0, vacuum value, right? And the H field, either inside or outside, is always I divided by 2 pi r. It's independent of the enclosed material, okay? So that's what we have to say about this lecture that was a little bit longer than usual, right? But I mean, that's how it is. So I hope to see you next time. Until then, bye-bye.